explain how we scaled our BI to handle billion records. Basically, how we updated our architecture and various components of it and everything. So to start with, I'll give a brief about Increff and what we do. So we are a retail SaaS company simplifying complex inventory management and supply chain challenges through two products. One is Omni Solutions and merchandising software. So to be more specific, Omni Solutions give offer solutions like warehouse management system, order management system, store fulfillment system, and couple of other supply chain solutions. And merchandising software is a platform, analytical platform, where we have our inbuilt patented algorithms for buying, planning, distribution, specifically for retail brands. And we serve both in India and for global clients as well. And Puma, Adidas, Reliance are like few of our biggest clients. So we'll deep dive into MS or merchandising software, where we recently upgraded our architecture to handle bigger scale. So this is the current overall architecture. I'll just quickly explain it and then I'll dive into BI specific architecture. So starting with data integration service, we have Data Factory, which we use to pull data from client ERP, marketplace, or SFTP, cloud buckets, or we have around 90 different connectors. Then moving to our data lake, where we use Parquet for which is again an open file format for storage, better efficient storage and faster reads. Then our third major component is our compute service, which is our core distributed compute engine, where all our algorithms, clients' custom algorithms are executed, and the outputs are visually represented in our superset. Now moving to BI specific architecture. So BI is one of the offerings in merchandising software, where okay, I'll go with the architecture. So once the data is loaded in our data lake, we transform it first, clean it and transform it based on our data warehouse specific schema using pandas. Then we were using a serverless SQL database earlier as our data warehouse, and then we were visualizing it through superset. So challenges with that, basically, our old architecture was able to handle the small scale BI workload. However, like recently we onboarded a very big client, maybe 5x of the scale that we were handling earlier, the biggest client that we were handling earlier. So with the old architecture, we were not able to handle that scale, resulting in, say, poor performance of queries, hit on our concurrency numbers and all that. So fortunately, we have been say following ClickHouse for a while, and we took this chance to do a quick POC and get it implemented within 2 weeks, and we went live, and it was a successful implementation. And currently we have tested it for 3x scale. Say currently we are the biggest client for which we are running at 1 billion records of the biggest fact table. We have tested it for 3 to 5 billion, but yes, we'll try to work more on that. Then new BI architecture. So the data preparation layer, where we were using pandas, we have replaced that with pandas plus DuckDB. So 90% of it is done through DuckDB. Then we have replaced our serverless SQL database with managed ClickHouse instances for now. And in the superset layer, like we have introduced Redis caching as well. Now, so basically these are the numbers or benchmarks, I would say. So earlier our scale was 200 million records, basically scale of our biggest fact table in our data model. We were serving 99% of our queries within 5 seconds, and 95% were getting completed within under 3 seconds, and 90% under 1 second. Now same, once we implemented ClickHouse, where currently we are handling billion records or around billion records, we are able to match the same latency. So basically this we had set it as a benchmark to ourselves, and we were able to achieve the same thing through ClickHouse. Plus with DuckDB also in the BI preparation part, we were able to reduce the preparation time by 70 to 80%, even more, but I'm just being conservative here. Yeah. So now coming to the interesting part, so I'll just go through the important optimizations that we followed throughout this implementation, right? So most important part, starting with data modeling. So currently we follow a fact constellation schema, which is also a star schema, where where multiple fact tables are connected to same confirmed dimension tables. Now in our case, we found that so basically data is stored at day level and day store and style level. In retail space, store and style is the commonly used granularity, and most of our dashboards required base data at week or month level, around 50-60%. So basically we have created aggregated versions of the same fact, say one fact at day level, one fact table at week level, and one fact table at month level, and same dimensional tables which are connected to all the 3 fact tables, and there are other fact tables also. So this is the overview. Now coming to one big table or completely denormalized table. So we are using OBT only for few custom scenarios where say we are not able to serve through our core schema. Major reason being we want to keep our core schema simplified and clean. So that is the major reason, and again I would like to add one more reason for not using OBT as the core schema. The reason is like our dimensions keeps changing very frequently, so maintaining an OBT will be an headache, so we went ahead with star schema. Then moving to partitions and primary keys. Yeah, in our case, order by is same as the primary key. Configuring it based on query patterns and say in the order of cardinality gave us the maximum data skipping and maximum performance upgrade. Then with respect to partitioning tables, yeah, so partitioning ideally should be done by analyzing your query patterns. Basically whatever columns that you frequently use for filters, maybe in case of a time series data, your day or month or week column will be the best to partition your table with, ensuring that data is distributed evenly within partitions to avoid performance degrade due to data skewness. Yeah, moving to write data types. Yeah, data types significantly influences compression. So we made sure that we are using the right data types when designing our tables. So few examples. One is low cardinality data type. So we have implemented it to most of our categorical columns in our dimensional table, and I guess as per the documentation, we did not test it out, but as per the documentation, if any categorical column having less than 10,000 distinct values, this data type will work best, but with more data, yes, the performance starts degrading. And one more example would be, say, in our previous data warehouse, we did not have the option to add unsigned integers as data types, and almost most of the columns were only positive values. So we took use of that, and yeah, initially we were just directly using int, and then we found that we can use unsigned it, and yeah, it gave a small performance boost. Now coming to query level optimizations, yeah, so maybe I'm not covering any basic query level optimization. So for us, we started with MySQL for business intelligence, which is weird by the way, but so we have been working with row based relational database for a while for BI use case. So our queries had to be that like so optimized that at least you get some performance out of it. So we were very good with query optimization. So I guess mostly we did not end up, or we did not find much on optimizing it further. But two things I will cover here. One is Jinja and Apache superset. So as I explained earlier, we are using Apache superset for our visualization layer. Apache superset has this cool feature called Jinja templating, where you can parameterize your queries. I guess this is there. Tableau has a very small way of doing it. I don't think you can do it extensively, but in Apache superset you can basically change, you can just avoid a join, or you can replace any part of the query based on certain actions. So we used Jinja templating wherever we felt a join can be made optional. Now I'll give an example. So generally joins on bridge tables are expensive than say normal fact 2-dimensional table joins. Now say if I have a filter on a bridge table, say on a column on a bridge table, which ultimately filters out the fact table, and I'm not using that column from bridge table in any of my visualization. It's just used to filter out the fact table. Then I'll just enclose it within my Jinja template. Basically I'll parameterize it, and when someone uses that filter, then that join part becomes active. But if nobody uses it, basically that join will not be active. And so with that we're able to see good performance in many dashboards. Then moving to pre-ware, interesting, this is the first time, like after moving to ClickHouse, this is the first time I'm hearing about this. So pre-ware is something which is enabled by default in ClickHouse, and it happens automatically. But okay, so more about this is like, say I have 4 or 5 columns in my where condition. I'm filtering out 5 different columns in my where condition. ClickHouse execution plan intelligently decides out of 5, say what 2 columns should be filtered out first, and then on top of that result set, the remaining columns will be filtered. So that is how pre-ware works, and this is already being taken care in the execution plan. But we found few cases where we checked the execution plan doing explain, and we found that maybe execution plan was not using the ideal column to filter it. So we started mentioning explicitly wherever we found that the execution plan is not optimal, and this greatly helped us in optimizing multiple queries and dashboards. Yeah. So now coming to future optimizations, even though we have tested or our current architecture for say 3x scale, there are several optimizations that we plan to explore and benchmark. So one such thing is projections. Again, something new for me and for our team, like we have not heard about this before started using ClickHouse. Materialized view, we know what it is used for, but maybe we are not using it right now because with our star schema, we are able to handle the expected load and response time. Then again, using dictionaries for joins, we will definitely, like, we'll have to explore this further, do some POCs and keep it ready when we reach that scale where it is really necessary. Then again, the final point is fully denormalized. Now, so I'll be closing with our future roadmap. Basically, the BI team's future roadmap at Increff. Prompt-based data extraction. I hope like almost every company will be working something on AI here and there. So this is similar to, I guess, AI assist feature in ClickHouse Cloud, but the intermediate outputs or final outputs of our algorithms are bit complicated. So we had to write our own RAG to say get the most accurate query. So we have already started work on this. POC is done. So soon we will be deploying it internally, and then probably it will come out as a feature of our product. Then maybe second phase of that would be say prompt based data visualization dashboard. As a end user, say if I have a query or if I want to visualize something, I'll just type and I'll get a visualization or dashboard created out of it. So we are still solutioning on that. We are trying to see how we can achieve that. Then open source ClickHouse implementation. So we are slowly moving towards cloud agnosticity. So I know that ClickHouse managed instances are already available in Azure, GCP, and AWS, but say still we would want to be sure that like if we have our own setup, like we can easily move it as and when required, or maybe the TAT will be lesser. Then final project that we have in mind is UI based file browser to manually upload or automatically fetch from external systems. So basically this will be part of kind of ETL. So we are trying to say give more custom solutions for the client. So ideal thing would be after having this is like customer can just add their data, upload their data in the browser, and then they can self-serve on our dashboard. Say basically any additional data which is not part of the schema or which is not already with us, they can just do it themselves and self-serve it on our superset dashboard. So so these are the points that I wanted to cover today. Thanks a lot. Any questions? Yes.
So regarding the data model that you mentioned, so you said that you are maintaining a fact
Constellation.
Fact
Yeah.
constellation schema. So and you mentioned that your facting essentially has three different versions which are different, like separated by grains.
Correct. Yeah.
So aren't you encountering some level of redundancy when you are doing like this? You can resort to a one big table approach and maybe have it separate.
But we are still fine. Storage is cheap. Compute is expensive. So maybe definitely we are just focusing more on the performance, and redundancy is just impacting the storage, which is anyway cheap. So we are happy to, and again as I said, people are moving towards OBT, which is completely redundant. We are still not okay with that, but this level of redundancy in the system is still fine.
Another question regarding distribution. So I'm not sure like if you have that in ClickHouse. So is it possible that so what we do in other warehouses is that we distribute a table based on either primary key or let's say if it's a dimension table, right?
Hmm.
Where you need it to get joined with multiple other factories, so you distribute that table across all the nodes. So do you control that sort of thing here? Do you implement any distribution
No.
style?
So ClickHouse Cloud doesn't work that way. So that is called as MPP style databases, which is massive parallel processing. Probably, I guess, BigQuery, Synapse, dedicated SQL pool, all these follow MPP style. But I guess ClickHouse open source implementation, you can still do that there, but I don't have much hands on there. But in ClickHouse Cloud, it's just a logical layer. So ultimately, data is stored in your lake as some columnar form. I'm just guessing or assuming it is Parquet only. Where ClickHouse has differentiated there is with their metadata management. So they have efficiently stored the data in memory so that you can quickly know which file to access. So ultimately, say if I'm talking about partitioning here, Parquet you can store it as partitions. So now ClickHouse manages that metadata efficiently. So whenever I search for a specific month, it has this information in memory and it knows where to look at directly. So that is where this is bringing difference with other. Maybe ClickHouse Cloud, I would compare it with something like Trino, or where we just have a SQL compute engine. It doesn't store any data, where storage and compute is decoupled. Same with ClickHouse Cloud as well.
Yeah, just now you were mentioning about the OBT.
Yes.
What is exactly?
So it's just one big table. So basically, a lot of people started, or a lot of big organizations started doing that. So generally, we have seen relational databases where you have 3 normal form normalization for normal OLTP or even higher than that. In case of OLAP, we were using star schema, snowflake, basically dimensional modeling. Now this is kind of a new thing, which is like not new. So they call it OBT, where your fact, dimension, everything is stored in a single table. So basically, say in case of retail, say we have style, this is a shirt, which category is it, which color is it, and this was sold, 10 quantity was sold in this day. Now I would store it as a fact table which contains all the sales related information. Then I'll have a dimension table for style and maybe for the location where it got sold. All these will be bifurcated. But in case of OBT, everything will be in a single table. Maybe that is evolving because storage has become cheaper. So you can, it's okay to have redundancy. But why we are not using that is basically our dimensional tables keeps changing. Since we are in retail space, with every 6 months, with every change in season, our masters change. So this dimensional table completely changes, and moving to OBT will have a very big overhead, maintenance overhead on our ETL tasks.
Maybe it's similar to denormalize, I
Yes,
guess.
dimensional modeling is also denormalization, but not complete denormalization. OBT is like completely denormalized.
Any reason why you were using DuckDB for BI data filtration, and did you plan any, if possible, if I give you the same problem, do you have any other databases in thought of?
So if you are looking for some, say, a distributed option, Spark, and there are a couple of other things, but say if you're not going into distributed, say just sticking to simple libraries like pandas or polars for data manipulation, DuckDB is the fastest that I have seen or whatever I have experimented. It's crazy fast, because something which was taking some 3-4 hours, we are able to run it in 10-15 minutes probably. And another advantage is, I guess more people know SQL than Python or Java, or so again you can just write a SQL script and do your transformation. So basically maybe that is the reason why we chose DuckDB. And one more advantage is it is in process, so you don't need to host it anywhere. I can just spin it up in a VM, as I am running the code, it's just a pip install in Python. It will start using the memory in process, in memory database. So you have heard about SQLite? So this is like OLAP version of SQLite. SQLite is OLTP, where you can install it in local also. Same way, even DuckDB can be installed in local and can be used to write queries on your local CSV files. Any other question?
Yeah. Why to use WDB? We have other options, like SQL Server.
No. So SQL Server. So this is basically just for your backend transformation. This is not. This will be replacing your ETL tasks or the transformation part of it. I don't know if we can use DuckDB for a front-end use case, but this is more back-end where you are doing some transformation using Python already, something non-distributed. Then DuckDB will be a very good option. Okay. Thanks everyone.
Thank you. Thank you so much.